Okay, so here we are at 6.7 empirical formula, and it goes along really well with 6.9 molecular formula, so I usually do those two together. You do need the file listed in the submodule, so if you don't, or you can write this out if you want, but if you want the bare bones file, then pause the video and go get that. So really, empirical and molecular formula are an application of moles. So we are always going to compare moles to each other. So whether you're given grams or the composition as a percentage, then one of the first things that you can do really in this whole entire course is calculate moles, and that will get you part marks. So when you have the two types of formulas, the empirical formula is the simplest formula. So it states the simplest whole number ratio, or the most reduced, which for ionic compounds is essentially the crisscross rule. But we sort of talk about the prefixes and don't really give any indication of how we come up with the molecular formula for molecules. But this is a quantitative way you can figure it out. Okay, so often the questions you're going to be asked are going to contain hydrogen, carbon, oxygen atoms. Those kind of atoms are present in molecules that can have they can have a simple whole number ratio, like an empirical formula, or they can actually be much larger molecules. So then that's where you would be calculating the molecular formula. Okay, so in our first example here, what is the empirical formula of a compound which has 2.2% hydrogen, 26.7% carbon, and 71.1% oxygen? So you can do these questions a variety of ways. The note does have a table in it. I recommend that you set up a table because it sort of makes your life easier, and you just do the math as like row 1 divided by row 2 equals row 3. So it makes your life a little bit easy and it helps to organize the information. When you are given percentages, we're going to assume 100 gram sample. So this is important because then that means if you have 100 grams and 2.2% of it is hydrogen, then that's 2.2 grams of hydrogen. 26.7% carbon is 26.7 grams. And why does this work? Again, when we did the lesson on percent composition, whatever this compound is, it always is going to have 2.2% hydrogen, 26.7% carbon, and 71.1% oxygen. Whether you have 50 grams or 100 grams, it doesn't matter. That's the whole value of percent composition and the value of comparing moles, all based on Avogadro's number. Okay, so we're going to take those masses, and like I said, every time you're given grams, if you would like to get part marks, then automatically change it into moles. So we are never, ever going to compare grams. And we talked about this in the second lesson of this unit when I introduced the mole concept. Because it's based on Avogadro's number, then that's a comparable quantity. You're not trying to compare apples to oranges. It's all based on 6.02 times 10 to the power of 23 particles. Okay, so the molar mass or the molecular weight is from the periodic table. So when you're figuring out what the formula of this compound is, we have no idea. So we're just going to use 1 hydrogen, 1 carbon atom, and 1 oxygen atom, and we're going to figure out how many of these atoms there actually are in our compound based on its percentage. So then we're going to change that into moles. So again, if you forget here, it is written as a formula if you are a triangle person. Moles is mass over molar mass or molecular weight. So again, when you do the table, it's like this row divided, and then you divide by this row, the second row here, and you get this row. That gives you the answer. Isn't that nice? Okay. So 2.182 moles, 2.223 moles, and 4.443 moles. Okay, so 443. Okay, so now these quantities as a mole amount, they actually look similar. Okay, so then you have, again, it's not based on how much space something takes up. So 2.2 grams of hydrogen doesn't, or 2.2% of a molecule, it doesn't seem like a lot compared to, say, 26.7% carbon, but carbon atoms as a percentage are larger, right? 1 to 12. So then again, how much space something takes up is not a good way to compare. So then we change it into moles, and we now can look at that mole amount and compare them to each other. So this last line here, this mole ratio line, that is the new thing essentially for this unit or this section. And all we're going to do is, I just have to switch here, is you're going to divide the moles by the smallest mole amount. Okay? So you can see these three asterisks here, they go with this. So you look and see why the smallest, because again, when you do empirical formula, it is the most reduced or the simplest. So how do we get that? Then you have to divide by the smallest mole amount. So you take a look, 2.182 and 2.223, they are pretty close. However, 2.182 is smaller. So each mole amount divided by 2.182. Okay, so when you do that, you get 1 here, you get 1.02 here, and you get 2.04 there. So those numbers aren't perfect. However, they're pretty close, not bad. So this means one hydrogen. And then when you have 1.02, that's pretty close to 1. And then when you have 2.04, that's pretty close to 2. So what happens is we're going to not worry about significant digits at all. When you do the mole amount, keep as many decimal places as you can. And you'll see in a second why there is a little, not problem, but a little exception to this when we round, which you'll see in the next box. So when you keep as many decimal places as you can in the mole line, then that'll sort of help. And then, so what happens is if you round differently than say the textbook or in a test question or something like that, you might actually get a different answer. So usually when I mark these kinds of questions, I have to take a look at your math and I use I figure it out myself to make sure that if your work looks right, then I'll check your rounding. Okay, so don't stress about that, but one of the things you can do is keep as many decimal places as you can, and then that helps to sort of not to sort of get the answer that maybe your friends do or whatever. Okay, or the textbook does if you check the solutions. Okay, so now we have to answer the question. So it wants us to find the empirical formula. We've done all of this work, and so make sure that you have some sort of answer statement. So what is the empirical formula? Well, we have hydrogen, and when you find the mole ratio, that tells you how many of each atom. So there's 1 hydrogen, which you don't have to write, but I'm just going to write it to emphasize it here. 1 carbon and 2 oxygens. Empirical formula should be the most reduced, so you can check. Can you divide any of those numbers by the same answer? No, you cannot. So that is definitely a most reduced answer. Okay, so rounding, when you round, like 1.02 is pretty close to 1, 2.04 is pretty close to 2. So what happens when you start to get towards the middle? So let's say you can round where necessary. So if it's 4 or below, round down, 6 or above, round up. But what happens when you are exactly at 0.5? Okay, so let's pick some random example of a compound that has A, B, C. Okay, and we do all of the work and we get down to the mole ratio line. So this is the only place where you're going to round. Okay, so mole ratio only. Remember, I said the other rows, keep as many decimal places as you can. Okay, so the mole ratio, let's say we get 1, 2, and 2.5. So now it's perfectly in the middle, okay? It's not 4 and it's not 6. So what do? Do we round down? Do we round up? Yes, normally we would round down, but that's, maybe in math. But here it's like perfectly in the middle. Can you have half of an A or a B or a hydrogen or a carbon? No, you can't. So the way that we remedy this situation is you multiply by 2. So if you multiply 2.5 by 2, then that will get rid of the decimal place. But you can't just multiply the C by 2 or whatever. You have to multiply them all by 2, right? What you do to one, you have to do to them all. So here we get 2, 4, 5, which is still an empirical formula. It's still the most reduced. Okay, but now we've handled that ambiguous 0.5. Okay, so all the other ones you can just round, but again, you're rounding at the mole ratio line, the last line. The other lines, keep as many decimal places as you can. Okay, so another type of question, so you could be asked to calculate the empirical formula straight up, or you could be asked which of the following are empirical formulas. So you're basically checking, are they reduced? And these are real things. C6H6 is a molecule called benzene, which maybe you've heard of. It's a very toxic, powerful, smelly industrial solvent. So and again, what you do to one, you have to do to them all. So can you divide this number and this number by the same thing? Yes, you can. You can divide by 6. So the empirical formula would be C1H1. So no, that is not an empirical formula. CH4, it is an empirical formula. It's already reduced. C5H10O5, those of you that are biologists, this is a ribose sugar. It has 5 carbons, and all of these can be reduced by 5 or divided by 5, whatever you prefer. So the empirical formula here really should be C1H2O1. This down here is glucose, which can be reduced to C1H2O1. So you'll notice here that they have the same empirical formula. So again, when you have an ionic compound, and that's not such a big deal, the empirical formula, often it is the same as the molecular formula. But tomorrow or the next lesson, when we do hydrates, their empirical and molecular formulas are also the same. Those molecules that have water molecules attached to them. But here, C5H10O5 is a ribose sugar, and C6H12O6 is a glucose sugar. And so these molecules actually exist in our bodies. Like our RNA is made of ribose, right? So glucose is the only food our brain needs. Everything gets broken down into glucose, these are real things. We needed a way to quantitatively figure them out. So what can we do? Well, we can further sort of analyze the the values we get and calculate what's called the molecular formula. So the molecular formula is the actual number of atoms in a molecule. So again, this is really reserved more for molecules, molecular compounds, as opposed to ionic. Okay, so and what you're going to do, you need the empirical formula. And you'll notice when we did ribose and glucose, in order for it to be a molecular formula, you could divide by the same factor. So what you're going to do is figure out this factor in order to get to the empirical formula. So you have to be given two pieces of information, or sometimes it'll say part A, percentages, find the empirical formula, and then part B will be, if the actual weight is this, what's the molecular formula? So, but you need the empirical formula, and you have to be given an actual molecular weight or molar mass. Okay? So if you look at the example here, the empirical formula, there's our first piece of required information. So there's ribose again, which we just talked about, and its actual molecular weight. So there's the second one. Okay, so we're going to compare the actual molecular weight to the empirical molecular weight and see how much bigger it is. Okay, so when you're calculating or if you prefer ratio, when we're calculating this factor, how much bigger is it, then it is bigger, right? The actual molecular weight is going to be bigger. So it always goes on the top, and then the empirical formula, molecular weight, goes on the bottom. So this you're given, have to be. And then the empirical formula molecular weight, again, sort of similar to the mole questions, you calculate this, right? It almost looks like we're not given enough information, but really by now, hopefully finding the molar mass or molecular weight from the periodic table is one of the first steps you always do, and pretty straightforward, okay? But this is why you need the empirical formula. Or like I said, in part A, you find it, and then part B, you use it. Okay, so when, and you don't need to memorize the periodic table, we'll give you that. Okay, so the actual molecular weight is 150 grams per mole. And then the empirical formula is CH2O. So decide for yourself how much work you need to show. And here it actually doesn't matter. You can round quite a bit if you want. And then you can see, 150 divided by 30 is 5. So the actual molecule is 5 times bigger than what the empirical formula says. So inside our body, when we do molecular compounds, you shouldn't really do the crisscross rule, because really strange things can happen once you start sharing electrons instead of transferring them. And here's an example of how to deal with that. Okay, so let's say you did this upside down and you did 30 divided by 150, you would get a decimal number, and you can't have decimal atoms. Like you would get, a decimal number that's less than 1, like 0 point something. So then that's your clue. Whoops, I did it upside down. So always do the bigger number on top, the actual molecular weight. And then again, once you calculate this molecular formula factor or ratio, that's great, but don't forget to answer the question. Okay, so now we have, I'll write the steps out in black again. So we're given the actual molecular weight. We calculated the empirical formula molecular weight. Now we have to multiply all the subscripts. Again, what you do to one, you have to do to them all. And when you do this step, again, if you're like, oh yeah, okay, I can see what this is going to be, you don't have to show your work, but I will here just so people can see where it came from. So empirical formula has one carbon times 5 is 5. Hydrogen times 2. 5 times 2 is 10. And then oxygen, there is 1. So the molecular formula is C5H10O5. Okay, so no longer is it a most reduced. However, this is really what the ribose sugar inside our bodies, in our RNA, that's what it looks like. Okay, thank you. Please do the textbook questions. Thank you.